Okay, let's continue with segment 3, which is basically we are talking about how to go from URS to FRS, and that's conclude this webinar. Basically, to do that, we need to generate FRS from URS. We need to build and review CCM library, and I will talk about that. Build a trend and assign IO to CM and CCM, add steps and transition, define enable logic, and add enable logics to these CM and CCM placeholders. Therefore, this is where we are, and we are following the footstep of the GAMP. Therefore, we are focusing on the FRS at this point. Therefore, if you remember, we talked about that we have these units. Some of them are master, some of them are copy. Therefore, we are generating these FRS that they have the FRS, the unit name, and it has a three type of labeling here that I will talk in the next slide. The things is important is some of our IO have been allocated as a sys IO, and in this project they decided if we have a sys IO, it should be in his sister. For example, if we have a sister IO here in C505, it should be represented in C505 as the tag name and SIS added to the name of the tag at the end. Therefore, and we need to generate this FRS for the sys units. Therefore, I think there's 5 tags here, and there are, as we said, 56 tags here, and 5 of them are sys tags. We're going back to our definition, and UM can have mode of operation steps, talks to equipment module, or talk to CM with the enable logics. Equipment module can talk to CM or multiple CMs, and equipment module can talk to complex control module, and complex control module here. At the end, everybody is just control module. Therefore, this is the overall hierarchy that we have. But let's come up with some rules that the parent module should be independent of the child module. For example, if I have a child module of a pump, then my distillation doesn't need to know whether the pump valve is opening or temperature is high or temperature is low. The parent module needs to say pump should be ready, or pump should not be ready, or pump should be running, or pump should stop. Not ready and stop majority of time are the same. And then at the same time, the child module should be independent of the parent module. The child module internally should not look at the temperature of distillation tower, or should not look at the level, should just communicate with the master in a very specific way. Otherwise, operators, you need to make sure they understand how we go from one to another and what's the mode of communication. There is no internal communication, because that becomes very, very confusing. And then the application should be single source, and application should be easy to understand and visualize. Now, if you think of a pump, let's just talk about it. Therefore, we know we have this CM that says digital in, and we know this pump can have 3 optional digital in. Feedback on run, whether the pump is running, feedback whether it's stop, feedback whether it's ready. We might have this, we might not. Depends upon the project and instrumentation team, which one they put in. Next, we have this thing called analog in. We had the CM, and a pump can have AI power, yes, or we can measure the horsepower, or we can measure the temperature. Therefore, in this case, we have the power. Therefore, we are measuring this. Therefore, we're using this CM here. And then a pump might have a DO command to say stop instead of just start. Therefore, this is optional again. Therefore, we have a DO start and a DO stop. Therefore, we have this one. Therefore, now we use 3 different types of CM, but we use them 3 times here, once here, once here. Now, if we send all of this information to our root tag, which is a DO, again, we had the DO here. Therefore, we are using all of these CM, we are putting them together in an environment, I call it complex CCM. which is a wrapper around all of these objects. And the difference between this and equipment module is this one does not have a step, it does not have mode of operation, and it's an entity to make the reusing of the objects much easier than what is available. For you don't program a pump over and over and over again. The same thing applies for example, complex control strategy. Here we have a control strategy that we discussed this before, that we have basically 3 measurements. These two can be the same, therefore we have a level and a level. This goes to the master controller, this goes to the direct level controller. The master controller controls the flow controller, which gets its AI from here. Therefore now we are using 3 cm of analog in. We are using 3 times PID controller, and we are using a selector, and we are using AO CM. Therefore, by putting all of these together under this wrapper, CCM MS direct control, then we can reuse this over and over and over again, and we test it once and we use it again and again. We just need to assign the AIs and assign the AO to it, that I will show later how we can put these things together. The most important part of every unit is how to design its trend. Basically, the trend is a way that you're going to define what is the steps and what is a control strategy. Therefore, if you look at this simplistic distillation here, that if you look at the feed, we are saying we have ready, fill, and start the cooling tower. Therefore, these are the state that we might have. It doesn't necessarily mean these are steps. Therefore, the way this tool works is you will document every time that you have anything going on. Therefore, as you can see, here is all of my MVs: steam, distillate, reflux, bottom, and cooling water. And here I open the feed and open the cooling water. This is to fill what? The bottom level. Therefore, if I just go forward, these are all of my CVs. Therefore, as you can see here, by opening the feed, I'm building the level, the bottom level, and I'm building the top level. Sorry, the labels are from the top. This is the feed. Therefore, here what we have is, this is the cooling water, and therefore we're just building the bottom levels. Therefore, we build the bottom level here. And next, we are going to start, if you can see here, we're going to start the steam to heat up. Nothing will happen, but the top level will start to get filling after some delay, because we need to get the vapor going up. And then we start the reflux and so on and so forth until we go to run, then we shut it. Therefore, this is very critical to draw this for feed, manipulated variable, and control variable. Can be a little bit complex. I didn't look at this for a year now. I need to remember the top is for this and these numbers and how they work. Very good. Therefore, if we go to the next one, then we have the IOs. Therefore, the IOs are defined per each unit. And now we want to assign IO to CM and CCM. If you use the tool or do it in the back of an envelope, basically what we are saying is that these are all of the root tags. Root tags are digital out and analog out. These are the way that we talk to the process. Therefore, it says that we have this many DOs and 1 AO. And then with the pull down menu, we go and allocate this one as a CCM block DO that we described. Block DO, block DO. This one is an agitator. This one is, again, master, slave, direct, level, flow, direct, level, control. And this is a pump. Therefore, we select these. we go and we say these are the elements, and we give it a generic name. This is critical because the generic name means, remember, we are going to build this library first with generic name, and then we are going to instantiate it with the CM names. Therefore, these are the CM names for it, and this is a GM or generic description of it when we build that library to be reused. Therefore, the first thing we assign all of our root tags, AOs and DOs, to their objects. Sometimes you don't assign it because, for example, if you have a DO start and DO stop, you just assign one of the DO to. If you have two valves, you assign one of the valves to the control strategy. The next thing we want to do is we go in from our library. We know that for this block valve, we have only DI feedback closed, DI feedback open. And we know from our knowledge of the process, therefore, we only have the first one, not both. Therefore, what we are going to do is we are going to allocate this one by pull down menu to DI feedback close element. And basically what we are building, we're taking this object, CCM objects, and we're creating this CCM objects that has a DI and has a DO, but does not have this DI. It shows it here, grayed out. And for the other example that we have, this one, we have a same block, but it's open, DI feedback open exists. Therefore, we select it, and basically we instantiate now these two objects, make or wrapper for ABV recycle. Therefore, this is the second stage of the allocating the IO to these CCM objects. Therefore, once we have defined all of the CCM objects, we go and define steps and transitions. And remember, steps and transitions are coming from our trends by combining different moves into one group, and we refer to them as the steps. Therefore, you need to think about it. The step definitions, again, we have a 4 hours discussion about that, the course, how to define steps and transitions. Therefore, here, what we have is steps are blue, manual transition are yellow, transition manual auto are orange, and these are automatic. And we discussed these in detail before. Now, the next part is the advantage of procedural control over loop-based control is that you don't go and put all of the alarms on, 6 alarms for every instrument, and then go and come up with alarm reduction systems and things like that. You just go and define alarms that you think they should exist by typing their set points here. Therefore, we say we should have a temperature bottom 120 and 140. Level low is 7, low is 10, 90 and 95. Again, these are examples, not real. And therefore, these are whether we have error in the measurement or digitals or we have mismatch. Therefore, once we define this in our IO page, then we go and we think about it, how we are going to enable them. Therefore, we talk about, for example, if you look at this agitator, we say the agitator should come in when we are filling and when we are running the process. The shutdown should go down. The control scenario, all of them should become enabled. Then this pump in, the suction should be enabled in fill, and because we are recycling it, and enabled in run. Therefore, by putting these simplistically E, as we discussed before, we say these are enabled at what step. Therefore, we connect the matrix of a step versus or CCM and CM enablement. Therefore, we have this. Therefore, as you can see here, this one is the product valve, this one is the level, this one is the second level, and this is our flow. Therefore, we allocate these to this, and basically we are missing the instrument names here. The instrument name shows up here. Very good. Now, if we go and look at the alarms, exactly the same things happen. We don't need to have alarm shelving. We don't need to have all of this sophistication. For each alarm, you go into this matrix and you basically specify whether the alarm is enabled or disabled. Once you have defined these two, then you go and generate these collection of CCMs or CMs. Therefore, as you can see, I have the pump in and pump out and recycle as a block valve. I have an agitator. I have an analog in for bottom temperature, pressure, and top temperature. And I have one for level control and one for a pump. Therefore, these are all of the objects I'm going to have to get this program going forward from FRS to next level. For the next level is that if you go and open this and look at it, all of the information that we've shown here automatically will go. Therefore, for the AO here, for example, that we define it here, this object here that is basically a copy of our CMAO. Therefore, it has the name, it has the level control description, what is the normal, what is the max and mean, and basically when is disabled logic, when is enabled logics, and so on and so forth. And basically it comes all the other stuff here. Therefore, we automatically fill in all of our CCM and we have this data available. Now, the next step is to take this data plus the other data we have and we build the code automatically from here. We have done this for a number of systems and we know how to do it, but this is beyond the scope of this talk. Therefore, in this talk, we talk about FRS to URS. We talk about building CCM libraries, building trends, assigning, and so on and so forth. Therefore, let's just try to answer some of the questions.